Hey, we're going to talk about part of the fundamental theorem of calculus today. And there are two parts of the fundamental theorem of calculus. And the reason I left this blank is because textbooks don't agree on what is part one and what is part two. However, in Googling and looking it up, trying to find a definitive answer, it does appear that most textbooks do call this part two of the fundamental theorem of calculus. I put a little question mark by there. It's really irrelevant what part it is. I do have a worksheet that I handed my students. It can be found at this bit.ly link down here if you want to print that as you follow along. It may make things a little bit easier. So let's talk about definite integrals and indefinite integrals. So if we have definite integrals, then it makes sense that there will be an indefinite integral as well. And an indefinite integral is any integral that does not have the limits of integration. Now, with a definite integral, the limits of integration tell you the x coordinates between which you are calculating area. And if you see an indefinite integral, it simply means find the antiderivative of the function f of x. So we're just finding general antiderivatives. And you should, if we are down to evaluating definite integrals, then you should be able to find indefinite integrals. And the antiderivative for number one, this is just a power rule antiderivative. That would be x cubed over 3. Or you could say 1/3 of x cubed. I prefer to do the whole thing over 3. The antiderivative of 3x would be 3, and 1 plus 1 is 2, so x squared divided by 2, plus the antiderivative of 1, which is x. And a general antiderivative, you should always be aware that there's the potential of a constant after that. And if you wanted to check that antiderivative, you would simply find the derivative of that answer, and it should take you back to x squared plus 3x plus 1. Which this will. And even if I did decide to add a 7 or a 12 or any constant, that constant would zero out in the differentiation process. So we put that C there. Number two, the antiderivative of sine x is actually negative cosine. A lot of people mess that up. Negative cosine x. And the antiderivative of 1 over x is the natural log of x. And we will always put that in absolute values to preserve domain issues between 1 over x and the antiderivative of 1 over x. And we'll put a plus c. So there's your general antiderivative, and you should be somewhat familiar with that process already. So let's talk about the fundamental theorem of calculus. And again, this is half of the fundamental theorem of calculus, and it is the method by which we will evaluate definite integrals. And so the conditions are that if capital F is any antiderivative of little f, and that can also be worded in the way that the derivative of capital F is little f, then the exact area under f of x, and under, we use that term loosely, it really means between the x-axis and the function of f, is this. So your definite integral from a to b of little f of x is the antiderivative evaluated at b minus the antiderivative evaluated at a. This is also known as the evaluation theorem. And so there is, in words, what the fundamental theorem of calculus is, and we're going to put that into practice for a few examples. So let's go on and talk about how this would be put into practice, because a lot of times wordy definitions are confusing, but you do need to remember that you're finding the antiderivative and evaluate the antiderivative at b minus the antiderivative at a. So let's look at this first examples. We have the definite integral from 1 to 4 of the function 2x minus 3 dx. First thing we want to do is find the antiderivative of everything between the squiggle s and the dx. Well, the antiderivative of x squared, of 2x is x squared. The antiderivative of 3 is 3x. And for this one example, I'm going to put a plus c because the general antiderivative should include that plus c. And then I need to evaluate that antiderivative from 1 to 4. The way we designate that in the written work is you can put a little vertical bar. Some teachers like to put like little brackets at the top and bottom. It doesn't really matter. And then we are evaluating from 1 to 4. And it would not be a bad idea. The reason I put so much space there between the bracket and the 1 and 4, it may not be a bad idea for you to get in the habit of writing x equals 1 to x equals 4. That is not necessary. However, there are methods of finding antiderivatives in which you very frequently will change the variable from x to something else, and you don't want to accidentally plug your original limits of integration, which are in terms of, in this case, x. You don't want to accidentally plug x values in for another variable, which is very commonly the variable u. So I'm going to write x equals 1 and x equals 4, and we plug in the top one first. So this will be 4 squared minus 3 times 4 plus a c minus, and then we want to subtract what I get when I plug in the 1 and make sure you get the second one completely in parentheses because it matters for the second one. First one doesn't matter. I like to put parentheses out of habit. So that'll be 1 squared minus 3 times 1 plus c. And after that, we have a lot of arithmetic to clean this up. And so that's 4 squared, that's 16, minus 3 times 4 plus c, minus the quantity of 1 squared minus 3 times 1 plus c. And if we keep cleaning that up, 16 minus 12 is 4 plus c minus, and this 1 minus 3, that's negative 2 plus c. So minus a negative 2 will be plus 2 minus a c. And you will notice in the evaluation process, when I plugged in 4 and plugged in 1 and subtracted those two values, the c's subtracted away. And they will always subtract away in the context of a definite integral. And so in this context, when you are doing definite integrals, you don't need the plus c, and I will not write it again after that one example. It's not wrong. However, it will always subtract out, so you do not need the plus c when evaluating definite integrals. In definite integrals, you better be writing that plus c because it is necessary. Let's also get a few more examples. Number 2, the square root of x plus 2, evaluated from 1 to 9. First thing I want to do is find the general antiderivative, except for the plus c. And for the antiderivative of square root of x, you want to think of that as x to the 1/2 power, and then we will apply the power rule to that. So x to the 1/2, we'll see 1/2 plus 1 is 3/2. And then we'll divide by that new exponent, which will be the same as multiplying by 2/3, plus the antiderivative of 2, which will be 2x. You could write plus c if you want to, but I'm not going to. I'm going to evaluate that from x equals 1 to x equals 9. And so that gives me, where's my pen? There he is. That gives me 2/3 of 9 to the 3/2. That didn't look very good. Plus 2 times 9, all minus 2/3 of 1 to the 3/2, plus 2 times 1. Okay. Now, if you are an AP Calculus student and you are preparing for the AP Calculus exam, hopefully you know that in a free response situation, this is your stopping point. We have all arithmetic. What I have written on my last step can be put into a scientific calculator. That would be acceptable in the world of free response. However, these are incredibly common multiple choice questions. So let's get in the habit of cleaning it up just for practice. And so 2/3 of 9 to the 3/2, that's the square root of 9 cubed. That's 27. Plus 2 times 9 is 18. So we have all of that minus 2/3 of 1 to the 3/2 is just 2/3 plus 2. Clean that up a little bit more. 2/3 of 27 is 18. 18 plus 18 is 36. Minus, I'm going to distribute that to that negative. And in these problems, I do not get a common denominator until I am absolutely forced to. So as long as I can combine stuff, 36 minus 2 is 34. I will combine everything that I can combine. And then when I can't do anything else, I will get a common denominator. 34 times 3 is 102. Yeah. So that's 102 minus 2 all over 3, also known as 100 over 3. Okay, so let's look at number 3. There's only one more example after this one. So number 3, we have secant squared of x minus cosine of x. And these are recognition antiderivatives. There is no process, no adding or subtracting or arithmetic involved. You should just recognize secant squared as the derivative of tangent x. So tangent of x minus the antiderivative of cosine x, which would be sine x. And this is the most common sign error in antiderivatives, is doing the antiderivative of cosine and sine. So I still, to this day, when I'm anti-differentiating trig functions, I will very quickly check that. So the derivative of tangent is secant squared minus, and the derivative of sine is cosine. So it'll be minus a cosine, which is what I started with. And then I'll evaluate this. from x equals 0 to x equals pi over 4. And we'll plug that in. So that would give me a final numeric answer of the tangent of pi over 4 minus the sine of pi over 4 minus, plug in 0, the tangent of 0 minus the sine of 0. And again, in a world of free response, that is an acceptable answer. But in the world of multiple choice, you'd have to clean that up. Tangent of pi over 4 is 1. The sine of pi over 4 is root 2 over 2. Tangent of 0 is 0 plus, distribute that negative. The sine of 0 is also 0. So we have 1 minus root 2 over 2. That might be how the answer is in multiple choice. It could also be written as 2 minus root 2 all divided by 2 if you got a common denominator. And all of these would be acceptable in free response world. Just remember, you don't have to clean up if it is a free response question. And that brings us to our last problem, the antiderivative from 2 to 4 of this product. And this is semi-tricky, especially if you're fairly new to the world of antiderivatives. Because what I have right here is a product. And just like with derivatives, where you have a product rule for differentiating, there is also a method for doing the antiderivative of a product. And that is a method called integration by parts. However, integration by parts is kind of tricky, and I'm going to avoid it for several reasons. One, in the world of AP calculus, integration by parts is a BC specific problem. So if you're an AB student and you see an antiderivative of a product in a AP style question, then you are expected to use another method. And parts will work for this. But the other reason I don't want to do this is even if I do know parts, which I do, it's still a heck of a lot more complicated than finding another option. And for this one, the other option is pretty simple. I'm simply going to expand this. I'm going to change this to the antiderivative from 2 to 4, and I'm going to FOIL that out. X squared minus 2x minus 3. And in expanding that, I turned it into a very nice, convenient power rule antiderivative. So that'll be x cubed over 3 minus the antiderivative of 2x, which would be x squared, minus the antiderivative of 3, which is 3x. We'll forget the plus c, and we'll evaluate this from 2 to 4. And so we'll have 2 cubed over 3 minus 2 squared, which I'm just going to go ahead and call that 4, minus 3 times 2, which is 6, minus 4 cubed over 3 minus 4 squared, which is 16, minus 4 times 3. What did I just do? I totally did that backwards. Blah! All right, let me fix that. Whoops. Let me ungroup that. This is an easy fix. Look, all you have to do is just grab that and move it to the other side. That was not very good. I probably spent more time just dragging this around than if I just erased it and started over. All right, so there's going to be the second part. You always plug in the top one first. So it's the upper limit minus the bottom limit. I didn't mess that up earlier, did I? Pi over 4 first. That's good. Let's see. X equals 9. I plug 9 in first. I think I did all this correctly. 4. Yeah, okay. So just a little brain fart there. And so now I'm going to plug in 4. 4 cubed over 3 minus 4 squared minus 4 times 3 is 12. Minus, and then plug in the 3. And we'll start cleaning this up. And like I said earlier, if I have denominators that don't simplify easily, 4 cubed is 64. 64 is not divisible by 3. I'm just going to leave that as 64 over 3. I am not going to get a common denominator until I'm absolutely forced to. Negative 16 minus 12 is negative 28. Minus 2 cubed is 8 over 3. Negative 4 minus 6 is negative 10, but I'm subtracting that negative 10, so plus a 10. And I'm going to combine what I can for as long as I can. 64 minus 8, I can combine my fractions. That's 56 thirds. Minus negative 28 plus 10. That will be a negative 18. And 56 over 3 does not reduce. And what you will find quite frequently is if you combine the things that already have a common denominator, it will end up cleaning itself up and you won't have to worry about getting a common denominator for the remaining terms. However, I do need to this time. So 18. So 56 over 3 does not reduce. 18 is 54 thirds. And so that'll be 56 minus 54 all over 3, also known as 2/3. And there we go. There's how you evaluate definite integrals. And once again, I'm going to keep banging this drum. Don't forget that in a free response situation, which these are often free response, they are more often multiple choice where you need to clean it up. But in a free response situation, do not clean it up at all. If you choose to clean it up just out of curiosity, then just very quickly after you're done, just X out your last several lines just in case it was an arithmetic mistake. And then the AP reader will know to look only at that last step. But again, in multiple choice, you will have to clean those up. So go ahead and clean them up when it's convenient and practice those algebra skills.